All right. A health product or a brilliant gadget? I thought it might be an interesting topic for this talk today because they seem very similar, but there are differences. And for me, it took me a while to realize that I want to build health products. So let's get into it. What do you want to build? Do you want to build a brilliant gadget or an invention or discovery? All of that is brilliant, but that's different from a product, right? Actually, I'm going to try to hide my face. Let's see. Seems okay. That works. All right. So I think you got to start with why, right? It's important to understand why you want to build a brilliant gadget or a brilliant discovery or an invention versus why someone would want to build a product, right? In there's a lot of commonality between the two, right? Like if you see at the bottom, both kinds of groups love to create, love to solve problems, but there are subtle differences, right? If you're talking about brilliant inventions and discoveries, they move the field forward, right? They might move the field of physics forward, like the theory of relativity, and you'll gain prestige for your brilliance. Everyone will be talking about how brilliant you are, how smart you are. On the other hand, if you are building a product, it's typically because you want to add value or utility to people now, right? It's relatively quickly. You want people to use your product, and your product may not be the most brilliant. It may not be the hardest thing to build, but it adds value to people's lives very quickly. And you would gain prestige still, but it would be for your hustle, right? On the gadget side, the brilliant gadget side, you do it because you love solving the hardest problems, right? It is the hardest problem, and then everyone knows that you solve the hardest problem that other people could not. On the product side, you love putting puzzle pieces together, and each of putting the act of putting together those pieces is not necessarily the hardest thing to do, except you're the one who's putting them all together, right? Um, so anyway, what I think is on the brilliant gadget side, you're trying to go deep. You are developing deep expertise in a certain field, which is what leads you to solve the hardest problems in that field, which seem superhuman to other people. Whereas on the product side, you tend to go wide. And you go wide and you do a lot of puzzle pieces type different actions together. You are not going deep in any of those areas, but you're necessary, you're needed to put all of those pieces together. So you got to understand a lot of different aspects. And you don't have to answer the question of, are you the person motivated by doing brilliant discoveries, or are you a person motivated by building products? Because it is a journey. It took me a while to understand, more than a decade to understand what I like to do. So you will have your own journey. Just know that you should find the answers to what motivates you and what that leads to, whether that's a product, or research, or a gadget. So I'll describe my journey and how I got to where I am. And by that, I don't mean my current position. I mean having the clarity of thought, of knowing that it is products that I like to build, products that I want people to use. I want these products to be in the health space, and just having that clarity is immense, right? Because I have it today, so I can spend the rest of my productive life focused on what I know I want to do, as opposed to, if I did not understand, I would still be trying to figure out, right, what I want to do. So all right. So I was always a geeky kid, I would say. I loved building things early on. I was a biology and math student in high school. But really over here, starting with my college, I went to college at DICT, Dhirubhai Ambani Institute. It's in Gandhinagar. And there, most of my coursework was focused on VLSI, and I was going deep in VLSI. A lot of my project work was focused on it. I knew at the age of 20, 21 that I was going to be a chip designer. After that, I went to Arizona State University for my master's. I actually went for my PhD initially, and that was also focused on VLSI plus analog. And I don't know if you can see the theme here, but I was definitely motivated by, brilliant or really the hardest problems to solve. And this was going further deeper in the chip design space. Fortunately, I ended up doing my graduate thesis on the topic of biosensors, and I worked in a lab with other folks from other disciplines. And so while I was going deep on the EE portion, because we built biosensor devices and I was responsible for the electrical portion, I ended up working with physicists and chemists and, of course, software. And so it was going wide on the other sciences. And that's really where I found that I loved building biosensors. I loved the concept of, being able to understand from outside of the human body what is going inside. Specifically non-invasive sensors, partially maybe because I am a chicken and I do not want to be pierced and cut. And so how much ever non-invasively we could sense things about the body, I wanted to do that. That was very fascinating to me. So that was important because I'm still in grad school and I discovered that I love doing this, right? After that, I ended up taking a job with Intel because definitely all of my coursework was all circuit design. I ended up working in lithography, which was seriously deep effort. At the same time, Intel was starting its wearables division, and all of the biosensors work that I had done for my graduate thesis was something that I was able to leverage to land a job in that team. And that was a really fun time. I would say the wearables period was probably 4 or 5 years. And I was definitely going wider on, I was building on top of the biosensors devices work that I had done in graduate school. So I knew how to build the devices, but in a sense, they were cool gadgets, right? They were not high volume production. They were not high quality products that somebody could use, right? They were really a few prototypes we would build, we do research, and we publish papers. So at the Intel wearables group, while I still worked on health sensors, I really got a lesson in high volume manufacturing, in operations, in human testing, and in working cross-disciplinary, going to China, working in factories there. So it was all very good experience that was going wider. And after that, I tried to spin out a startup because Intel was going to get out of the wearable space. And my team and we had invented this ECG and blood pressure device, which seemed like it is too cool a gadget, too brilliant a gadget for us to not try to turn into product. And this was encouraged by Intel's venture arm as well. So I felt like there was a lot of support for me and my team to try to spin this company out. But in pitching to venture capitalists is when I really started to grasp this concept of this is a gadget and it's not a project. It's not a product. And that became clear because when VCs were asking me questions about how are you going to go to market, who are you going to sell this to, who is the customer, I realized I hadn't thought through any of this. I had just, we had built something that was really hard to do. Many papers had been published on it, and people had been trying to solve this really hard problem for a long time. And it just felt like we had solved it. So we should turn this into a product. And if we just built something so cool, somebody would buy it. And that's not how it works, right? You need marketing. You need to create a market for something. You need to make a product exactly for the customer. I'll talk more about it. But the distinction between a gadget and a product was really starting to become very clear when the possibility of having your own company became real. So after that, I made a very clear pivot to be able to understand how to build essentially a product or essentially a business, right? When I say product, I mean something that somebody would buy and pay money for. So after that, I took a role in Intel's Olympics team doing business development. This was Intel sponsored the International Olympics, and I got to go super wide in different in different areas like artificial intelligence, drones, 5G, augmented reality, virtual reality. And to me, what I wanted to focus on was customer acquisitions, doing deals, negotiations, really understanding that aspect. And it, what the specific industry that I was focused on was less important to me. The customer acquisition portions were more important to me because I had realized that I just didn't understand that. After that, I ended up moving to Intel's healthcare team, doing strategy, product, and marketing for them. And this was me going deeper into the healthcare industry and essentially wider on the functions because I had not really done strategy, product, and marketing functions. I was just trying to round out my skills. The healthcare industry is very interesting because typically in consumer or even enterprise business, you think about who pays, who benefits, and who chooses, right? And think about a consumer, it's usually the same person. It is a consumer. A consumer will buy a product because they benefit and they are the ones making the choice, and they are the ones who are paying for it. Whereas in the healthcare industry, at least in the US, it's the three different players who are doing three of these actions. So if you make a product, typically a patient would benefit, the doctor would choose the product and prescribe it to the patient, and the health insurance company or the employer would pay for it. So it's really, all three of these parties make it a very complex space to sell something in. And which is why it's good to go deeper on the healthcare industry if that's where you want to build products. Which leads me to now. I've recently joined AliveCor. I am the VP for product management. And if you haven't heard of AliveCor, it is a startup. It's about 100 people. And what we build is this handheld ECG. It's very small. It can be in your pocket. It's an ECG device, and you could put 2 fingers on it and it'll record your ECG and you can send it off to your doctor. It also, we also provide care plans and other products. And obviously, we're building many more future products, which is why I have a job. So if you don't know of the company, it's very innovative. Do check it out. All right. So if you do want to build a product, how do you define the product, right? And what does defining the product really mean? It really just means, what are the features going to be? What is it going to look like? But how do you get to that point? And I think you've probably heard many people showed like different ways of doing it. So there's this thing called the business model canvas. It has these, I think, 9 different, 9 different things to think about: the partners, activities, resources, etc. Similarly, there's something called a product management canvas. And again, it talks about many of the same things that the business model canvas has, plus features of the product. But if you really think about these canvases and think about how to fill them, I think the simplest way to do it, and I think you've heard it said by many people, is you start with the customer, right? You always start with the customer. The first thing you want to do is think about who the customer is and what their pain points are, and you have to address the pain points, and that has to be part of your unique value proposition. And that kind of leads to your must-have features. What is part of your minimum viable product? What are the features you have to have? And of course, you go through the market opportunity sizing, positioning, you think about your go-to-market plan and what is it going to take to create the product. But always start with a customer. And I'll kind of walk through this sort of exercise with one of the products from my past. So the example I want to talk through is BIOSPORT. It started off as a gadget because I built a gadget that I thought was very cool. But then, of course, eventually, with the help of a lot of other people and a full-blown team, it became a product. And I'll talk through what it took. But, this was the concept. The concept was I used to run, and I wanted to track my heart rate when I ran. I typically wore a chest strap that tracks heart rate. And the thing with the chest strap is, A, it's cumbersome because you gotta put it on your chest. B, you have to make sure that your device is charged, and you've got to wet the chest strap sometimes to make sure that it's making good contact with your skin so that it records your heart rate. It's just a little cumbersome, right? Plus, you already many people, at least I did, already wear headphones when they're running. So if you could just measure heart rate inside of the earphones or earbuds, then, we would solve a particular pain point for somebody like me who was a runner. And so I ended up it started off with this concept. This is me trying to take like an ECG from the ear. That did not work. But that's just metallic tape. But eventually I ended up putting optical heart rate in the ear, spent about a year on that concept, built out an app, built a really low power concept. And a year later, I was able to show this off at Consumer Electronics Show. And, I had solved essentially a very hard problem. A brilliant gadget is what this was. The hard problem I'd solved was I had reduced the power consumption for the optical heart rate module that was going to be in the ear to so low that it could just run off of the power that was supplied for the microphone. And that was a really hard problem to do. It hadn't been done before. This kind of gadget did not exist in the market. So I was like, oh, really cool. We solved the hardest problem. It's done. But it was not a product at that time because, there were literally only 5 prototypes of it. And I'll talk about what it took to take it to an actual product, right? Like that ships in a box and people can buy it on Amazon. There's marketing, there are ads, there are articles. Other people are using it, sending reviews. So let's talk about that a little bit. So let's go through the same things that we saw before. With when you think about a product, you think through the customer, the pain points, etc. So for this, who is the customer? I think the customer for this was someone very much like me, someone who wants to exercise and run. They also typically listen to music, and they're a little bit of a quantified selfer. They want to quantify how their bodies are doing, right? So they want to know whether they're exerting too much or not exerting enough. And this is typically a younger consumer. So somebody in your 20s and 30s. So that's your fit young runner consumer. That's the customer. Then let's think about the pain points. Like I described, other methods to measure your heart rate, like even Apple Watch or other watches. Let me not say Apple Watch, but all other watches. They're not super accurate during a workout because when you're and because I've worked with optical heart rate before, and actually many optical heart rate watches, the wrist is not a very good place to get your heart rate signal because the arteries are buried deeper and the signal is much stronger in the ear, right? So the one of the pain points is various methods to measure heart rate during a workout are inaccurate. Other pain points are, another pain point is if you want really accurate heart rate and you use a chest strap, that's a fairly cumbersome process. The third, I would say, pain point could be the fact that all of these devices need to be kept charged. Otherwise, you could be ready to go for a run and discover that there's no charge in your device, so you can't use it that day. I'm sure there's other pain points, but let's just say there's these three. So what do the unique value propositions have to be for our device? Well, I'd say the first one is, this is not an extra device. Many people use music to run and wear headphones and earbuds. And so this is incorporating an additional functionality they wanted in a device they already have. The other big one is it does not need to be charged. It gets power off the audio jack, which is fairly unique. No other device does it, which means that they don't have to worry about keeping the devices charged. And it's very accurate because in-ear heart rate is much more accurate because ears are pretty small and thin, and the arteries have to be very close to the surface of the skin. So when you use optical heart rate, you get a pretty good signal. So that's a unique value proposition. Must-have features must include your unique value propositions, must address the pain points, right? So I hope you're seeing that everything's flowing down from the customer, and all of these flow down from the top. So must-have features, no charging required, should be very, very accurate, because this customer really cares about tracking their accurate heart rate, right? Otherwise, there's no point to having a device like this. What else, right? Think about this person. This is a runner. They sweat. They probably run outside. They could be running outside or inside. So at least you need to make this device waterproof, right? Because they're sweating. They probably go for a run in the rain. You want to make sure it's waterproof. If they do run outside, then there's going to be sunlight. There's going to be sun and shade. And, sun has a lot of optical energy, right? So typically in an optical heart rate sensor, if you take it out in the sun, it'll drown out your complete signal. It'll saturate your input amplifier, and you won't be able to see any heart rate anymore. So you want to make sure that you design for some sort of automatic gain control so you can reduce the gain significantly. Point is, the feature that you want to have is whether they're in the sun or the rain, you should be able to get accurate heart rate. So that's a must-have feature. What else? It's good. Another thing we had on this was we had tangle-free cords, because these cords get tangled up, and when somebody's running, you don't want those tangled up. The other thing that's not really necessarily all part of the unique value proposition, but were features that we added, was think about what kind of music people listen to when they are exercising. It's typically high energy, high beats kind of music. So if you think about the frequency response that your headphones or earphones should have, if you're building them for someone who's going to listen to a symphony, the frequency response is going to be very different, right? And if its response is lower on the bass side, it probably doesn't matter as much as somebody who's running and there's a lot of bass and there's a lot of beats in that. You want to make sure your frequency response is amplifying those parts of the audio spectrum. Let's see. I think that was it. I would say those were the minimum features. Market opportunity size. There's many ways to do it, right? First, you could look at the size of the market for people who use chest straps to accurately measure their heart rate. Or you could say, it's really much bigger than that, because if you put heart rate measuring in earphones, you could really look at everybody who exercises with headphones. So you can get market reports. You could probably just Google some initial numbers, and that's you've got to figure out who are you targeting and then try to find numbers for that market. Let's see, positioning. right, for this one, we're going to position it very much like this is a must-have device for any person who's exercising and cares about their health. Because it's a no-brainer. And typically in positioning, you also think about what are you competing against, and you typically have to say this competes against this other earphone that does this, but ours does it better. In our case, we really didn't have anything to compare it to. We basically just had to be like, oh, one of a kind, must-have device. So I guess that's both good and bad, because when you have something to compare it to, people know how to perceive your offering. Let's see, next one, the go-to-market plan. Yeah, you got to think about how is this going to go to the market? Where are you going to launch it? So for example, we've launched high luxury, fashionable watches. For example, we launched them at fashion weeks. We've launched things at Paris Fashion Week, New York Fashion Week, something like this, which is really, an electronic, cool electronic gadget. We ended up launching at the Consumer Electronics Show. So you want to think about where your launch event is going to be. You want to think about what media outlets you're going to announce through. You also want to think about where is it going to be available. Think through the logistics. Is this going to be at a Best Buy, or is it only going to be available online through Amazon, through your own website, through Flipkart? So you got to think through how you're going to market. You might also want to think about which countries and regions it's going to be available at. So that's what the go-to-market plan is. And then key resources, right? So for really any product, but almost even individually for features, it's going to cost you something, right? If you want to implement a cool new feature that requires, like a really smart, like genius who's going to come up with an algorithm. And if you skip that feature, you're not going to require that genius, and that genius is really expensive. Then you want to think about whether you can afford to have that feature or not, right? So you got to think about, so for example, let me go through this device, just what I said I was going to do. For this, obviously, we needed electrical engineering teams. We needed an optical designer. We needed mechanical designers. We also needed a partner to go to market with, right? This is not an Intel branded product. This is an Intel Inside product. So we needed a business development person to go find us a partner. Yeah, so you got to think through all of the resources you're going to need. All right. Okay, so I have the slide. I'm not going to go through all of this. I just want to flash this up because, this might help you guys think about the products you are working on, right? Or if you got these really brilliant things that you've built and you want to turn them into products, you should think through this lens. But just think about the first one over here, right? Fossil. Think about the customer this represents. So the two things on the side, they were targeted at women, and the watch in the middle was targeted at men. These are all smart devices. So they all, at least do like a buzzer and notifications so that you can check your phone. And, this is designed. So for example, the Fossil thing, it's designed for sophisticated people, young professionals, typically 30 years, 40 years of age. And I think it's clearly visible when you look at the industrial design and the product, right? The products are all very similar if you think of them just from an engineering perspective, because they're all really smart watches. They're all like a microcontroller inside, and they've got Bluetooth connectivity to your watch. They all have haptics. They can all just do a buzz and show you the notifications. But they all are very different, and it's very clear when you look at them who their customers are, and therefore the features will be dictated by what those customers want. The thing on the right, like Tag Heuer's watch, versus the thing on the bottom, the New Balance watch. They're very similar watches, but the person wearing the New Balance watch is going to be running outside in the rain or shine. They're an athlete, they're very, very fit, and they really care about tracking their heart rate perfectly, right? It can't go wrong. The person wearing a Tag Heuer watch, which is a luxury brand, and costs probably 10 times as much as the New Balance watch, they're mostly going to be not moving as vigorously, right? Like I imagine an older man, perhaps like 50s or 60s, on a sailboat or, playing golf, right? And their heart rate, like the accuracy level of their heart rate, isn't as important. Plus, it's not as challenging to do because they're not moving very much, right? So you determine what the features are based on the customers. I know I've been saying this repeatedly, but really the customer determines the features. And the last one I wanted to show you was like an example of a really cool go-to-market plan. So we launched this high luxury item at New York Fashion Week. This was called the Mika, I think, bracelet, we called it. And we did it in partnership with a brand called Opening Ceremony, which is such high fashion luxury that I had never even heard about it. So, but the go-to-market plan was launching at various fashion weeks around the world. Okay, so this is I just put these here for you to have examples. All right, so because this is a technical conference and a technical audience, I thought I'd walk through how optical heart rate sensor works and the principle and the engineering of it. So I'm switching gears, right? I'm stopping the conversation about product versus gadget and how do you determine features, and switching over to the technical details of the optical sensor itself. So the principle itself is fairly rudimentary. You have a source of light that you shine into your skin. Some of it gets dispersed. Most of it actually gets dispersed, probably 95%, and about 5% of it will come back and hit your optical sensor. And this is what you are perceiving, and that signal kind of looks like a pulse, so you can tell somebody's heart rate. So that's really, the principle is very, very simple. And this is a reflectance-based thing. You can also just, anyway, that's fine. The principle is very simple. But if you see the gears that are on the right, when you try to turn something like this into a product, you need like all of these just different disciplines to work together. You need optical simulations, mechanical, electrical, you need algorithms, data collection, and human trials, because you got to collect data on the human beings. So we started with building a human skin tissue optical model, right? Because you are trying to design the best optical housing, which maximizes, so if I go back for a second, which maximizes how much light will go into your tissue, and you want to optimize your sensor placement so that the most light comes back out, right? How good this signal is will really depend on how much light you're able to put into the tissue and how much gets reflected back out. And of course, you can build 1,000 different prototypes and test it on people, or you could do it this way, which is where you kind of take human tissue, you build an optical model of the tissue, and each of those have, and you can run your simulations on it. So that's kind of what we do. We run simulations. So the top left, the bottom is the skin tissue. That's the model that we've created, and the top portion kind of shows where the two LEDs are that are producing the light, and the sensor is in the center. And you can see most of the rays that go into the skin tissue just get reflected, or they don't come back to the sensor. In fact, very, very little light actually comes back to the sensor in the center. and how far you put the LEDs from the sensor, how much the optical separation is. So, you know, between the sensor and the LED, you need to make sure that you have very opaque walls, right? Because you don't want light leaking directly from your source to your sensor, because obviously that's going to be a lot higher than the light that comes back from the tissue, and all of that is just noise. It's not the signal you're looking for. And then, of course, after you've got the most optimal geometry based on many optical simulations, you feed that into the mechanical design. So what we feed into the mechanical design is, you know, this is how far the distance should be. This is between the LEDs and the sensors. This is how far the LEDs and the sensors should be from the skin. Obviously, you're trying to get them as close as possible to the skin, but you typically can't, because you have to have, you know, the enclosure and transparent windows, and you've got to have walls between the sensors and the LEDs. So you're trying to get as close as possible. There's also leakage sometimes, optical leakage through the, you know, the transparent glass or plastic enclosure that you have right next to the skin, and you want to try to minimize that as much as possible. So you feed your best optical design to mechanical engineering. And so in this case, if you can, you know, we built essentially like a wall and enclosure. There's a little bit of foam. So our sensor is completely optically isolated in the center from the two LEDs on the side. So because we've got wall all around our sensor, no light can go back through leakage within the device. All the light that's going to go back into this device will go through the tissue, or, you know, if like people are wearing the device very loose, it might go in between the space between somebody's tissue and the device, but there will be no leakage within our product. At least that's what this mechanical design shows. So obviously, you know, it's not always as simple. Here's the most optimal placement that we found based on optical simulation, and then the mechanical team will come back and say, well, this cannot be built, right? What you're asking for is either too small or too fine, or the tolerances are too low. And so it's an iterative process. They'll come back with what is the next best thing they can build. Then that has to be simulated again. And then we try to find the most optimal mechanical design that is buildable or manufacturable. After a few iterations, obviously, we, you know, reach some sort of design that is reasonably manufacturable and does not cost a lot, or at least, you know, the investment is worth it, right? When you talk about the resources needed, you could probably improve things more, but at some point the return on investment is not worthwhile. After you have the mechanical design, that kind of, you know, dictates the optical layout, right? But that's just the layout piece of it. I'll talk a little bit about the design itself. You know, I don't mean to go into all of the schematics here, but really the, you know, important pieces here are, you've got your amplifier that is connected to the light sensor, and that amplifier has digitally controlled gain. And the reason that is very important is because, you know, the example where I said somebody runs into sunlight. Now, if you run into sunlight and the intensity of sunlight is so much higher than the intensity of the very few rays of light that are being reflected from inside of your tissue, it completely drowns out, you know, your ADCs, your analog to digital converter that's connected ahead of this amplifier. So you've got this amplifier, you've got an ADC in front of it, and the ADC can, you know, there's a dynamic range. And the reason you want to have a digitally controlled gain is because as soon as you step out and it's like completely DC saturated, because you can tell that somebody stepped out in the sun, your firmware will have to go and change the gain, reduce the gain to a level where now your ADC can again start recording. Sorry, I got a phone call. Will again start recording the reflected light. Okay, so that's really the important piece. I mean, I'm sure that there's a lot of optimizations that I can't really get into. All right. Sorry, I'm just getting this phone call. All right, so yeah, the next piece is very important are the human trials, right? So you can design the best device optically and mechanically, but sometimes you got to test it on people, and sometimes it'll uncover things that you've never seen before. So we would, and you also need human trials to actually collect data, right? Because so far you got only raw data. You have to develop algorithms that that run on that raw data. But an example of what might be uncovered in a human trial that we wouldn't have thought of before is, say, the optical sims came up with the best optical placement, the mechanical team went back and forth, and we've come to a conclusion that we can build this really nice device. But this device turns out is really high. Like the Z height of the device is very high. And so the center of gravity essentially is pretty high off of the wrist of somebody. And then when we actually put it on a human being and they start running with it, that's when we realize that it shakes too much, right? That's when we realize that we didn't take into account that it would shake on the skin when we were doing our optical and mechanical design, right? So then we have to reduce the height, we have to make it wider. So these kinds of things do get uncovered in human trials. We had certain protocols. We had indoor protocols, outdoor protocols, to be able to spot all sorts of places, all sorts of edge cases where where our algorithms were failing and we weren't able to calculate heart rate. So that yeah, what else? Oh yeah, these are my really cool team members collecting, doing all the protocols and collecting data. The picture on the bottom right, she's my good friend and colleague, and what we're doing over here is we're trying to collect the most accurate data. So we bandaged up the devices so no light can go through, right? Because when you're collecting early data and developing early algorithms, you want the cleanest possible data. We're trying to get data like this, but unfortunately, data is only clean when you're still. So let me show you an example. So the top graph here is what's coming in through your analog to digital converter, past your amplifier, past your light sensor. And the second graph is the accelerometer data. And whoever's wearing it, the subject, is still till about 200 seconds. And you get pretty clean data, optical data, until that point. And then they start doing some sort of regular motion at about 200 seconds, and the data gets dirtier. And then they start doing more irregular motion past like 400, and the data is all over the place. It's just jumping up and down. And because it's optical, when somebody moves in a periodic manner, it kind of looks, and the device moves on their hand, it kind of looks very similar to heart rate because it's periodic, right? So if I'm running at the same cadence as my heart is beating, or at a cadence that is reasonable for the heart to be beating, on the optical signal, you do not know whether your pulses were caused by a person moving and therefore the device shaken on their hand, or if it's actually because their heart is beating and this is actually their blood pulsing. Let's see. So this is what the spectrogram looks like. We take all this time domain data, convert it to normalized frequency, and typically what you want to do, if somebody's sitting completely still and they just have their heart beating, the only signal you'll get is their heart beating. So if their heart is beating at like 70 beats per minute. When you convert it into the frequency spectrum, you are going to see one clear yellow line, as you can see from the in the first before 200 seconds point, one clear line at 70 beats per minute. And that's it. Your frequency peak at 70 beats per minute is their heart rate. It's very simple. But what happens right after the 200-second point, when they start moving, you have no peak. Now from this signal, I can't tell what someone's heart rate is. And there's energy all over the frequency spectrum. So let's see how we tried to solve that problem. Sorry about that label at the bottom. So algorithms will help extract heart rate from the data. And let's see how we implement these algorithms. So this is a graph of, this is a raw graph converted in the frequency spectrum. And I can see 3 peaks, right? And I can't tell from the 3 peaks, if you look in this part of the section, which one is their heart rate, right? There are 3 peaks that are equally strong. So then I can look at the motion data. And when I look at the accelerometer data in the in the y-axis and the x-axis, I can see that this x-axis data shows up as a frequency peak in the raw data, as well as this y-axis data shows up in that raw data. So what my algorithms do is they remove these 2 artifacts, and then I end up with a cleaner signal where the motion artifacts have been removed. And this can be done in some of these cases. There are definitely cases where motion's all over the place where you can't do it, but in the durations that you can come up with a very clean heart rate signal. So we put it all together, all of our optical, mechanical, electrical, algos, data, human trials, and that's kind of what leads to building like a full device and a full product and a heart rate module in a product. Well, that's it. That's really, what I wanted to talk about. I want to say thank you and all the best. I know we don't have questions since this is a recorded talk. You can find me on LinkedIn if you would like to reach out and ask any questions. And I also wanted to thank Professor Anil Roy and Sanjay Chaudhary. They have, they're my teachers from when I was in college. This is more than a decade ago, and I know they're organizers of this event. So thank you, professors, for this opportunity. Okay.